Okie dokie. All right. All right. So today we're going to be continuing our discussion of quantum mechanics, physics 660, and I'll add we're going to be always starting every lecture by review of the previous lecture. So this is your opportunity to ask questions regarding what we went through in the last lecture. I put this to the side, I think. All right. So review of lecture 1. In the last lecture, we discussed 2 experiments, namely the Stern-Gerlach experiment and the double slit experiment. And the point of these 2 experiments was to point out that there are some observations that we see. There is an experiment that produce results that we cannot explain using classical mechanics, classical physics, and they absolutely necessitate a departure from classical physics. And no matter how counterintuitive, we'll have to invent formalism to describe them. And all right, so what were these experiments? The Stern-Gerlach experiment was a measurement of spin. So we, for example, said we're shooting silver atoms. Silver atoms have spin, an intrinsic magnetic moment that some atoms have, for example, silver atoms. And we were sending these through magnetic fields, and because the magnetic field had some gradient in, for example, z direction, the atoms with different spins would respond to this. They would either bend upwards or downwards. And this was our measurement. We rotated this from measuring the z-axis to the x-axis and the y-axis, right? And then we repeated this in different configurations. That was the content of the Stern-Gerlach experiment. So the first observation, the first lesson was that was surprising, was that the results of SZ and SX, for example, came out to be quantized. Atoms would bend either up by a certain amount or bend down by a certain amount. This is counterintuitive because if the spin is just some vector in a 3-dimensional space, as you project it to the z-axis, you expect to find all sorts of different components in the z directions. However, we're always finding a quantized answer. Quantized means that it comes in discrete values, right? So in this case, 2 options. It was either plus h bar over 2 or minus h bar over 2. H bar is a constant, or well, it is a dimensional constant that has unit of angular momentum or action in physics. So as I said, if you have any questions as a review, please ask. That was lesson 1. The more important lesson, which was somewhat shocking, was the statement that we could not measure SZ and SX simultaneously. To make that point, we went through this setup where we first measure SZ, discard the bottom component, the one that had negative h bar over 2, keeping the top one, then send the top the plus h bar over 2 for SC through SX, discarding the minus, keeping the plus. And then at this point, you would think that you would have, if you could simultaneously measure SZ and SX, you would think that this beam that you had here, the select set of atoms that have gone through both of your filters, would be SZ equal plus h bar 2 and SX equal h bar 2. But we send this through SZ again, and surprisingly, we found sometimes the atoms would come out with SZ minus half. So this was very, very surprising. And we also, so this was one thing. So we seem to be finding that we could not simultaneously measure them. Then there was a double slit experiment. So this experiment is really old. This goes back to the early days of quantum mechanics. The second experiment is called the double slit experiment, which was a thought experiment that's been going on and physicists have used for a long time. But it was actually realized in the past couple of decades as the quantum technologies have improved. And the point of this double slit, let me just describe it quickly. We send atoms through double slits, right? And what we are finding is that if we don't observe which slit the particle goes through, what we see here is an interference pattern, but which is inconsistent with the picture that the particle goes through either here or there. It's inconsistent with the particle picture, and it really suggests a wave nature for this propagate this what we thought was a particle. However, the moment you modify the experiment just by making an observation, sending a laser that would measure which slit the particle goes through, this interference pattern is destroyed and is replaced by the particle pattern, which is just sum of two. So you would get just something like this, which is what you expect from the particle behavior, right? So the point of this experiment, not only it confirmed this picture that measurements could affect the behavior or characteristics of the particles, I guess, degrees of freedom. Different measurements could affect each other. Measurements now could affect the measurements in the future. Like the properties we thought we knew about the I guess system. But this experiment also highlights the particle wave duality, meaning that what we thought was a particle, an electron, sometimes behaves like a wave, sometimes behaves like a particle. And this really depends on what properties do we measure. Similarly, light, which in classical physics we considered it to be a wave and not a particle, shows the exact same behavior. Sometimes it shows wave behavior, sometimes it shows particle behavior, depending on what we measure. All right, any questions about these two experiments we went over last time? Okay. So to summarize, these experiments challenge classical physics by demonstrating first or zeroth order, certain observables are inherently discrete. They're quantized. And this is surprising. This already tells you that spin is a very different quantity than angular compared to the classical angular momentum that we think of as a vector in space, right? Then one lesson is that lesson number one is that what we measure, what we know about the state affects its future behavior. What we measure today could change the results of the future measurements. Said differently, it's impossible to simultaneously know the results of certain measurements. Of course, if you measure SZ, the Z component of the spin, and repeat the same measurement, you still reproduce it. So actually, it's not just SC. Sometimes there are some measurements. We're going to be talking about that. So let me just tell you in advance. Some measurements in quantum mechanics, it would be impossible to simultaneously know the results. Such measurements, we're going to call them incompatible. Some measurements, we can know the results simultaneously. We're going to call them compatible. So compatible measurements, they seem to fit our intuition of classical physics. The surprise here is that certain observables, such as SZ, SX, are a pair of observables, a set of observables that are incompatible, right? So the existence of incompatible observables, measurements, forces us to abandon our classical point of view. Good? Any questions? All right. So we built on this observation. We saw that we said that we've seen something like this before in the polarization of light. That light, as it propagates as a wave, it has a polarization, which is say it's propagating in the z direction. The polarization is defined as a vector in a two-dimensional perpendicular space. So, for example, if it's propagating in the y direction, it's in the xz direction. And then we talked about the z polarized light, x polarized light, 45-degree rotated polarized light. And we saw that light behavior how it passes through these filters, actually can reproduce this bizarre physics we're observing in Stern-Gerlach. So from this, we just concluded that we could use the vector representation, the mathematical framework we use to explain polarization, to explain spin. So what is that mathematical framework? We describe polarization by a two-dimensional vector, right, in the xz. Here, we're going to use two-dimensional spaces to describe spin. Then we talked about how these two-dimensional vectors have to be complex, right? This had to do with the fact the analogy with waves was the existence of circularly, I guess, right-handed or left-handed polarized light, which requires a phase shift between x and z component. Here, we're in the case of SZ and SX seem to suggest you need two-dimensional vectors, but the fact that you had SY, we learned that we could arrange for that, at least at the moment heuristically, by making our vectors complex. So we're talking about to model spin of this silver atoms, which we're taking two values, two outcomes, two independent outcomes of plus h bar over 2, minus h bar over 2. We are going to model that by a vector space of two-dimensional complex vectors. We're going to call that a two-dimensional Hilbert space, sometimes called a qubit, right? In general, if a measurement is quantized with d-independent outcomes, for example, instead of plus h bar over 2 minus h bar over 2, you could have 0, h bar, and minus h bar. Those are three independent outcomes. Some atoms actually have that behavior for their spin. Those are spin one of atoms or objects. That could be modeled by three-dimensional complex vector space. In general, if you have d-independent outcomes, we're going to model them by d-dimensional complex vector space, namely a d-dimensional Hilbert space, a qubit. So is it clear now what the d-dimensional Hilbert space is? I'm motivating it. We're going to get to the mathematical definitions in a bit. Now, in quantum mechanics, some measurements have infinite independent outcomes. For example, the energy of an electron that orbits the nucleus of an atom has a countably infinite number of outcomes. You have heard about this. Was there a question? Okay. If there are questions, please ask. You've learned about, hopefully in your quantum mechanics, undergraduate quantum mechanics, you have learned about the orbitals and how electrons that orbit the radius, the nucleus of, for example, the electron that orbits a proton, the nucleus of a hydrogen atom, will take discrete values of energy, quantized values of energy, parameterized by an integer, which is a positive integer, runs from 1, 2, 3, 4, all the way to infinity. So there are countably infinite number of outcomes for energy of an electron that orbits a proton in the hydrogen atom. We're going to model that by an infinite dimensional complex vector space. We're going to call that Hilbert space. Good. So every time I say Hilbert space without specifying the dimension, very likely I'm talking about the infinite dimensional case. Now, here's a little comment. We're going to come back to this later, but I just want to say it to get it straight for now. As a quick comment, we're going to get back to it later in a couple of lectures. Sometimes some measurements seem to have uncountably infinite independent outcomes. For example, a continuous set of outcomes. For example, the position of a particle that moves on a line naively seems to suggest that the position is a continuous variable, and position, we don't think of it as quantized in quantum mechanics. So it seems like we should have a continuous worth of independent outcomes. Now, such a thing is physically is an idealization and physically unreasonable. So the Hilbert space is still countably infinite dimensional, and we'll see how we'll explain this phenomenon as these in the language of this Hilbert space and what is going on, right? But I just wanted to point out that even though it seems like the position of a particle is a continuous variable, and when you measure the position of a particle, it comes out as a continuous variable, uncountable, infinite set of outcomes, is actually an idealization. All right, so that's just a comment on the side. We're going to come back to this later. We don't need to worry. You don't need to worry about continuous variables for now. Good. Any questions? I'm assuming there are no questions. All right. Are we good? Yes, no? Someone?
Yes.
Yes,
Okay,
I'm good.
Thank you. Thank you so much. Okay. I just don't know like all the all right. So so now we're gonna start lecture 2. That was so far a review of lecture 1. In lecture 2, we're gonna talk about Kets, bras, and operators. This at this point, I don't know how much you'll learn about this language in your undergraduate level quantum mechanics, but this is more than anything else a very beautiful or efficient or nice, pleasant, pleasant to work with notation invented by Dirac to work with complex vector spaces. All right, to work with complex vector spaces, or AKA Hilbert spaces, right? So Ket and bras, this is a notation. This is a convention invented by Dirac. You don't, like none of this notation, even I don't know if it's scary or not to you guys, is really represents nothing but a complex vector. I was already using this notation, right? S of z plus h bar over 2. And then I said this is a 2-dimensional vector, right? So good. Now, most of today's lecture is going to be about building this notation. Now, it turns out that this is an extremely convenient notation to the point that it gives you really a conceptual advantage, a huge conceptual advantage. All right. So in quantum mechanics, we use this d-dimensional, sometimes d is infinite, complex vector space, namely Hilbert space, that describe our sum of our states. So this is important. I say sum of our states. So what are vectors representing in quantum mechanics? These are representing some states, okay? So these are complex vectors. If you wish, you could just denote them with alpha, a vector sign over it. But this is a more convenient notation, as you will see. Like complex vectors, a vector space, in a vector space, you could add vectors. Here's where I'm adding 2 different vectors that I'm labeling by alpha and beta. You could multiply vectors by complex number because it's a complex vector space. And when you multiply it by complex number, it doesn't make sense whether you put the number on the left or on the right. It's just a number, right? So a complex vector space basically has an addition operation and a multiplication by a number, a complex number, scalar. All right. Now, here's a physical postulate. So now I'm going to add some more physics. So far, I said that vectors in this Hilbert space represent some states. Now I'm going to say that, oh, these vectors are called Kets, right? I'm going to say 2 Kets that are the same up to a complex number represent the same physical state. So this is a principle. 2 vectors that are just that are parallel to each other, but the only difference is that one of them is longer, right? Or it has an extra face sitting in front of it. They represent the same physical state. So in the mathematical terminology, what we are talking about are not vectors in the Hilbert space as states, but they are rays. Ray just means that like if you have a vector, it's only the direction that counts. right? Not the length of it or the coefficient that sits in front of it. Said differently, the overall phase the complex number, overall complex number that sits in front of the vector is unphysical. The only thing that is physical is a relative phase. This is a comment for the future. For now, you don't need to worry about this, but you will see later that this is going to be important. For now, these two Kets represent, when C is a complex number, represent the same physical state. Is that good? All right. And observable will be observables, things that we measure. Observables are things that we observe, right? Are going to be represented by operators, aka matrices, right? We call them operators because in a d-dimensional Hilbert space, these are d by d matrices. When the Hilbert space is infinite dimensional, the proper term to use is not an infinite by infinite matrix. The proper term to use is an operator. We're going to see soon that observables are not all operators. They're special operators called Hermitian. But for now, don't worry about it. What we're talking about I guess the statement is that every observable is modeled by an operator. They act on a ket from the left, the same way that the matrix acts on a vector. Oh, these kets are like column vectors, right? So if you have a matrix that acts on this, it will be acting on the left. This matrix acts on this column vector from the left by matrix multiplication and produces another column vector. So this is an observable that acts on the state and changes it to some other state. We said that observables can influence states, right? So this is how we're going to represent it. You could use the vector notation like this. It's ill-advised. The good notation to use is Dirac notation, which is A ket alpha. A is the operator, right? We usually write it this way. This is multiplication from the left. So this, the fact that the bracket, this is half bracket. So the idea is this. Yeah, okay, good. Any questions?
Yeah, I've read that it's incorrect to think of Kets as the physical states because when we go to the density formulation, which is more general, they don't uniquely represent the same states, so it's wrong to think of them as states.
Very, very good. So that's why I have the word sum. So rays or Kets represent some states, but not all states are Kets. That's what you're saying. We're going to get there. Good.
One more thing add to that. If the ket has like infinite dimensions,
depends what you're trying to model. Depends what you're trying to model. If you're modeling the spin of silver atoms, as we saw, that object could be modeled. Spin has Sx, Sy, Sz. These are the only independent measurements you could perform. And that could be modeled by two-dimensional complex vector space, a two-dimensional Hilbert space. So we're going to use a 2D vector for that, two-dimensional Hilbert space. If you're trying to model something with infinite number of outcomes, for example, the state of an electron that orbits the center of the nucleus of hydrogen atom, then you'll have to have infinite dimensional spaces. It's a question of the system you're trying to model.
So then would the operator look different?
Sorry, what do you mean?
Just having a hard time imagining an infinite dimensional matrix as like an operator.
For now, don't worry about it. For now, don't worry about it. For now, what I want you guys to know is just D by D matrices. If you can imagine D by D matrices, we're good for now. We're gonna get there. Are there any questions about D by D matrices as operators acting on vectors, and Kets are column vectors? So the idea is that these vectors represent some physical states, right? Up to this constant, right? This phase complex number that sits in front of them, that's unphysical. And observables are going to be some of these guys that act on the left. Good? I have to say this. Sometimes I postpone some comments to later, and you will see I'll do this a lot in this course, perhaps more than a regular course. The reason is that quantum mechanics is so counterintuitive, and there's so much so much abstraction you have to get used to, that it's better to do it one by one, like gradually. If you want to start talking abstractly in the most general setup, as mathematicians do, you wouldn't be able to understand the first page of definitions of quantum mechanics. One of my goals is actually to, after the first third of the course is over, to be able to get you guys to a point where you could just pick up some abstract book on quantum mechanics,
Sorry?
read the axioms of quantum mechanics, and make sense.
Type C? Lightning?
Sorry?
No, Lightning. Sorry.
Excuse me. Sorry. Other questions? All right. Good. All right. I'll continue. If there are questions, ask. So, of course, as you act with a matrix, an operator on a ket, on a complex vector, the result is not going to be proportional to the initial vector or ket. And if it is, we're going to call that ket the eigenket of that operator, right? The same way that we had eigenvectors, we're going to call these, so complex eigenvectors that are of complex matrices we're going to call them eigenkets, right? So this is a super compact notation I'm going to be using, right? So I'm going to represent, so here's an operator, right? Acting on some ket that and then this is the eigenvalue, right? And this is the eigenvector. I'm going to label the eigenvector with the eigenvalue. And the A refers to the fact that the operator was A. It's a super compact notation. And I'll tell you the caveat to it right away. There are some situations where that would get yourself confused. But perhaps this textbook that we're following is one of the cleanest textbooks. The reason is that it uses this ultra compact notation. So it's very important that you get the notation first before trying to go further in the book, right? So here's an operator. I'm going to represent I'm representing the operator with capital letter. I'm representing its eigenvector with just like, not capital letters, and labeling the eigenvectors with their corresponding eigenvalues. Remember that eigenvalues are just complex numbers, right? So I'm labeling this. Can someone see what is the caveat to this? Where can I get, what is it that, when is it that this notation is confusing? Any thoughts?
Like when it's degenerate, or there's degeneracies, I think.
Exactly,
right?
Exactly. Degeneracies. When there are two inequivalent vectors that have the same eigenvalue, this notation is going to be super confusing and actually pretty bad. So in those cases, this notation has to be modified. We'll get there when we discuss degeneracies in quantum mechanics. But for now, this notation is compact and assumes that the outcomes, there are as many outcomes as these eigenvectors. They're independent outcomes as the eigenvectors. Good? Any questions? I am trying to go slower than the last lecture. So I think last lecture I just cruised through a bunch of things and I ended up with like a couple of minutes extra at the end. So please do ask questions. This is, the foundation of it is very important. A lot of this is like basic linear algebra. I shouldn't call it basic. This is linear algebra. And I absolutely recommend that you work through it. If you feel that these eigenvectors, eigenvalues, you're not comfortable with it, I absolutely recommend reading this book. This is by far the best book I know. Linear algebra done right. So this is perhaps the best textbook you could pick up to familiarize yourself with linear algebra and just catch up. Good? All right. Now let's use this terminology before going further to just describe this Stern-Gerlach business and spin of silver atoms. So what were we measuring? We're measuring an observable. That observable we're going to represent by a matrix, 2 by 2 matrix. Why 2 by 2? Because the results of these measurements of spin, in the case of silver atoms, had two independent outcomes, plus h bar over 2, minus h bar over 2. Now, the vector, which had the plus, I'm going to represent it this way, as z plus. We did this, use this notation before. And when sz is measured in this state, it gives you h bar over 2, and the state doesn't change. If we measure it in this, negative h bar over 2, you get minus h bar over 2, and the state doesn't change. So the outcomes we're reading were the eigenvalues, and the states that were coming out after the measurements were the eigenvectors, right? Is this notation clear? Or am I making a leap? So if I'm using the notation of this compact notation of A, I'll be representing these with plus minus h bar over 2. Is that good? And
Yeah, I
as I
think it's
said
good.
many times, sorry, good. As I said many times, the dimensionality of the Hilbert space is the number of independent outcomes. Good. All right, so that was Kets. Those were column vectors. What about row vectors? So those are called bras, and they're the bra space. The reason is that when you take the inner product of a column vector, when you multiply, actually, like inner product here is matrix multiplication, a row vector with a column vector, you get a number. That is the inner product. So inner product is a number. The idea of Dirac was that we're going to call that a bracket, split it into two parts. We're going to call the bra as the row vectors and ket as the column vectors. So we'll get there, but I'm just telling you in advance what it is. So a general vector is going to be, you could write it as a sum over these, for example, independent eigenstates, right? In this case that we're discussing, we had the sz plus sc minus. So these were spanning, providing a basis for the two-dimensional vector space. So I can take a general vector in this two-dimensional complex Hilbert space and write it as a sum of these, right? So think of this, think of it this way. I think we wrote these last time as z minus 0, 1. So alpha is going to be c plus c minus, right? With this notation where I'm representing this as 0. Oh, actually, sorry, I'm calling this plus and minus. Good. Everyone follows me? This notation. So this is summing. The sum runs over all eigenvalues. In the case of SC, the sum runs over two ingredients. I guess I've been talking about D-dimensional Hilbert space, so I should put D here, not N. All right. Now, the bra space, for those of you guys who are familiar with mathematical terminology of vector spaces, is the dual space of the Kets space. If this doesn't tell you anything, just don't worry about it. Does anyone know actually what the dual space is? Out of curiosity, any math-oriented person who knows the dual spaces?
Yes. It is the space of linear operators acting on the original vector space.
Linear functions, the space of linear functions. But anyway, all right. Functions from this space of numbers. All right. None of that is required. It's just if you're math oriented, you might have seen this concept of dual space before. I'm just making a connection. So what does this mean? This dual space. It means that for every ket, for every column vector, complex column vector, there exists a bra, which is a row vector. There's a one-to-one correspondence, and this correspondence is through what is called conjugate transpose. It sends the ket alpha to bra alpha. What is it doing? Well, let me tell you in advance before making it super mysterious. If these were real vectors, the operation we're talking about is transpose, right? The operation for real vectors would have been transpose, right? So this under transpose becomes C plus C minus. However, it turns out the right concept for complex vectors is dagger. What is dagger? It's transpose. It has two steps when you take the dagger. First, you transpose, then you take the complex conjugate, right? So there are two steps. You transpose and take the complex conjugate of each element. But clearly, this procedure associates to every ket bra, right? To every row, column vector or row vector, and vice versa. You can go back, right? So the conjugate of a conjugate is again the same vector. So it's squares to itself, to identity, sorry. Now, this dagger operation, we're going to be using it over and over again in quantum mechanics. So it's just a complex, the analog of transpose and complex Hilbert spaces, complex vector spaces, Hilbert spaces, which on top of transpose, you also take the complex conjugation, because these numbers need not be real. These are complex vectors. Complex vectors means that the elements are complex one by one, right? Complex, real plus imaginary parts. So under conjugation, conjugation is builds a one-to-one correspondence between kets and bras. It goes both ways. This conjugation preserves is linear, meaning that if you add two vectors, we said that this linear vector space of kets has two operations, adding vectors. Under conjugation, the maps are also added, so it's called a linear map. And it's, well, sorry, not linear, it preserves this. But if you have a complex number multiplying alpha under conjugation, it sends alpha to the ket, it's C star. That's not surprising, because I told you that you take the transpose and do this. Is this step clear? Such a map is called an such a map is called anti-linear map. Good. So for example, what is I0 dagger? This vector is minus I0. Good. All right. Any questions?
So here in anti-linear, like anti refers to the fact that you're taking a conjugate.
Yes, your complex conjugate, correct.
Yeah, okay.
If it were linear, it would just be the complex these numbers would just come out, right?
Yeah.
The fact that, yeah, exactly, precisely. Now, this whole terminology is invented because of the following. If we have a row vector multiplying by a column vector, you get a number, a complex number, right? Which is called a bracket, because you put a bra next to a ket, you obtain a bracket. A bracket is a number, a complex number. And the way that it works is just matrix multiplication, right? Apply matrix multiplication to rows by columns. Now, can anyone see already why we introduce, well, okay, no, I don't need to make you guys do guesswork. This is called an inner product of a bra and a ket, right? So inner product of a bra and a ket is a bracket, which is a complex number. It has the following two properties. First of all, the bracket of alpha and beta, ket beta bra alpha, is the same as the bracket of bra beta ket alpha complex conjugate, because these are numbers, right? These are complex numbers. Furthermore, the bracket of alpha and alpha is positive, not negative. Does anyone know why we had to introduce for complex numbers on top of transpose, had to introduce a complex conjugation? I've given you enough to be able to guess that.
So I don't think you'll satisfy the second condition of the inner product if you don't
Precisely.
do the complex conjugate.
That is exactly why. If you have real vectors, let's say two-dimensional real vectors, these are real numbers. If you define the bra in real spaces as the transpose, you take the transpose with the same of the inner product this is going to be R1 squared plus R2 squared. So this is positive, non-negative. The reason in complex spaces on top of transpose, we have to take complex conjugation is that when we have this, when you take the transpose C plus star, C minus star, now the inner product remains positive, right? Because this is just C plus squared plus C minus squared. Now, why do I want the inner product to remain positive? Well, actually, that's one of the axioms of inner product. That's what an inner product is. But does anyone know why I want this object to be positive? What's the interpretation of this object? What was the interpretation of this object in the case of real vectors?
We need it to be
It's length.
positive because it's related to the probability of each state existing. So
No, just imagine this is a real vector, two-dimensional real vector. This sum, what does it calculate for you?
It's the length of the vector.
Exactly. It's the length squared. It's the length squared of the vector. The reason we want the dagger, the inner to be complex conjugate, transpose and complex conjugate is that we want to interpret this as a notion of length generalized to complex vectors. This is precisely the reason, right? The inner product gives you a length, notion of length. Now, just to introduce jargon, for these complex vectors, this length is called norm of a vector. Good. So think of this as the length squared of this complex vector, and we want the length squared to come out positive. Therefore, this condition. Now, based on what I told you, if we have a bracket of a vector which is 0, we call this a null ket. Does anyone know what is a null ket like? Like a two-dimensional null ket. Tell me how to write it. So this has to be equal to 0. The only way to satisfy that as complex numbers is 0, 0. There's no other way of satisfying it, right? If I had not taken complex conjugation here, I would have had crazy null kets. I would have had some vectors that were not 0, 0, but had 0 length, right? All right, any questions? We're good? Okay. I'm assuming that you guys will ask questions. Let me just go through this slide and then I'll stop for questions again. Now, consider two kets, alpha and beta. We say these two kets are orthogonal if the inner product is 0. The bracket is 0. So I'm using the word inner product and bracket interchangeably, right? Now, this should also not surprise you because this is a simple generalization of the case of real vectors you're familiar with, right? When v dot w, where this is a row vector and this is a column vector, would give you 0, you would interpret that this guy is perpendicular to this vector, right? Is that clear? Is this familiar? Okay.
Yes.
Good, thank you. Thanks. This is the disadvantage of Zoom classes, and I apologize. But all right. Now consider a vector that is not null. So what I can do is that because C times that vector for some complex number, I said describes the same physical state, it is sensible that I get rid of C and talk about, because C really controls the length of the vector. When I take, or some complex number that sits the length of the vector, exactly. So what is the C alpha? What is the conjugate of C alpha? It's alpha C star. So when I take the inner product, this inner product, what I obtain is C squared length of norm of alpha. So this C really just controls the norm of the vector. And I said the norm of the vector is unphysical. So let's just normalize every vector to unit norm. How are we going to do that? Here's a ket. I'm just going to first calculate the bracket alpha alpha, which need not be 1. If it's not null, I can take the square root, and it's not 0, so I can divide by the square root. I'm going to call this norm of it. I already called that, gave it that name. I introduced this vector. This is a normalized vector. Why? Because when you calculate this bracket, it comes out as 1. It has unit norm. So these states that I've been talking about in the Hilbert space we want to represent, this is a convention. We're always going to normalize them to take them to be unit norm because there's no physics associated with multiplying the vectors by numbers. Good. So here's a good moment to pause. Are there any questions so far? What have I described so far? I've described the ket space. This is the space of complex d-dimensional vectors. I've described the bra space, which is these are complex d-dimensional row vectors. There is the dagger operation that builds a one-to-one correspondence between the two. It's the composition of convex transpose and complex conjugation. That we define the notion of norm as a generalization of notion of length that had to be non-negative. And we define inner product, which is this matrix multiplication of a bra with a ket. It gives you a number. Good. Any questions? All right.
Oh, I have a stupid question, like how to spell that if bracket alpha beta equals 0, the word on the left top, right top, or so.
It gets orthogonal.
Yeah.
This
So
is our if this happens, this is our sorry, you asked what is this word? I'm sorry, my
yeah.
handwriting is horrible. My handwriting is horrible. I apologize. Also, I have to change the tip of my iPad pen. That is
Thank you,
also
got
something
it.
else. All right, thank you. Sorry about that. By the way, no question is stupid. This was particularly my handwriting, so it's my bad at all. I apologize. All right, any other questions?
I have 2 similar questions.
Yes.
Paragraph in the middle of the slide here, it says always as something that starts with an N.
Normalize. Sorry.
That's what it is. Okay. And then also that line over the alpha symbols. I don't know what that means.
The line over. This is just tilde. It's a new notation.
Oh, okay.
It's just alpha tilde. I'm just like, I didn't want to introduce a beta to give you guys the impression of a brand new vector. Yeah, if my handwriting is not legible, please ask. Any physics questions, hopefully, or maybe math question? This is Ket. I was giving a talk actually 2 days ago, and somebody complimented me on my handwriting, which has never happened in my life. So, all right. Operators. This is my attempt at writing operator. So now we're going to be talking about operators, which we're going to use to describe observables. We said that observables. So here's just to start. Let me give you this. I told you that vectors describe states, but not all states are vectors. Some states are represented by vectors. Observables are represented by operators, but not all operators are observables. So keep those in mind. I'm going to actually clarify this issue, this line very quickly in a bit. All right. So I said that these operators act on Kets from the left. That's just matrix multiplication. We say two observables are equal if x equal y. If x equal y, meaning that if the as matrices, element by element, they're equal, we call these the same observables, right? So this map from observables to operators is sort of like doesn't have a kernel. That's a too massive way of saying it. Okay. If an operator acts on all Kets and gives you 0, we say that operator is a null operator. So in a two-dimensional Hilbert space, tell me what is the null operator? It's 0, 0, 0, 0. It's the only matrix that if I multiply it by any vector, I'll get 0, right? So the same way that I define null Kets, here I'm defining null operators, right? You'll see the point of this. This at this moment it seems like stupid definitions, but it will be useful in the case of degeneracies and some setups that we're going to be interested in quantum mechanics. I added vectors, Kets, I added bras. Here we also can add operators, right? Let's focus on addition first. Adding two operators is a commutative operation, meaning that x plus y is the same as y plus x. How do you see that? Simply, the statement is that when you take matrices and add them up, you add them element by element, right? That's commutative. Commutative means that you could change the order. It's also associative, meaning that if you first add y plus z, y and z, then add the results to x, that is equivalent to adding the x and y first and then adding z. This is associative. In the case of matrix addition, these are trivialities. These hold, but I'm saying because as we go to more fancier operations, I want to use this terminology. Good. So operator additions, by the way, I'm motivating everything using finite matrices, but there was a question earlier. All of these properties I'm listing, we're going to generalize to infinite dimensional setups. We're going to say operators have these properties, right? Kets are going to be, every equation I write here, all these equations will generalize to the infinite dimensional case, and that those cases we're not going to be talking about infinite dimensional vector. We're going to be calling it a ket, and everything I'm writing will generalize, right? So this addition operation for operators, addition of operators is going to remain commutative and associative and all that, right? Good. I'm just highlighting the mathematical structure you need to abstract out of D by D matrices to generalize and talk about infinite dimensional Hilbert spaces. All right. Most operators we're interested in are linear. What is a linear operator? These are operators that act on C alpha alpha plus C beta beta. C alpha comes out, alpha, C beta comes out. Right? This is the result. Such an operator is called a linear. In this course, every operator we talk about, explicit operator we talk about, is going to be linear. Notice that dagger that I introduced is not an operator. That's not a matrix. That's an operation. Right? Here, an operator, all of the operators we're going to be talking about are going to be linear, except one. There's only in this course, I'll only talk about one anti-linear operator that's going to be time reversal, and it will come up in the second half of the course. So for now, all operators we're thinking about are linear. That's why we're modeling them with matrices. It's easy to convince yourself that matrix multiplication is a linear operation. Hence the name linear algebra. An operator can also act on a bra from the left, because you could multiply a row vector. Sorry, from the, no, I get my left and right confused, from the right. Because you could multiply, if you want to multiply a bra by a matrix and get another bra, you have to multiply from the right. And the interesting a consistency check is that the action of X on a ket, when you take the dagger of it, that's like the action of X dagger from the right on the corresponding bra. You could convince yourself this holds. This is a consistency condition. Right? So I can act on the Kets, take the dagger, or I can, that's equivalent to just acting from the right on the bra. Good? Very good. Now a definition. An operator is Hermitian. I apologize, my handwriting is, at least for new words, I have to write them properly. An operator is Hermitian or self-adjoint if X is equal to X dagger. So what is X dagger for operators? Any thoughts? What is it? It's the same operation. It's transpose followed by complex conjugation. So if I have I should not use, I do not overuse A. Gamma 1, 1, gamma 1, 2, gamma 2, 1, gamma 2, 2. What is the dagger of this? The dagger of this is, first I do transpose. Transpose means swap these two guys, don't touch these, right? So swapping these two would give me 1, 2, 2, 1, 1, 1, 2, 2. Then I take the complex conjugation here of element by element. I take complex conjugation. Good. So from this, you immediately see that, so we define an operator to be Hermitian if it's equal to X dagger. Can you see what is, are there any special properties that you can see from this definition, what I showed here, about the diagonal elements of Hermitian operators?
They're real.
Yes, because the only way for these two to be equal, this to be equal to the original one, it doesn't give any is that gamma 1, 1 and gamma 2, 2 have to be real. Good. So that's something you can see. So this is Hermitian. We can multiply operators, but now multiplication of operators is non-commutative. XY is not the same as YX. Matrix multiplication is non-commutative, right? Famously, yeah, that you could check. However, it's associative. If you multiply YZ and then multiply it from the left by X, it's like multiplying XY first and then multiplying the right by Z. You don't have to specify an order. That's associative. Now, this is, I guess, I should have given this as a homework. I might give this as a homework. Just check that this is true. That XY dagger, the whole thing dagger, is like Y dagger, X dagger. Actually, can you guys see why this is true? Let me just do it. So as a matrix, what is this? This is XY dagger. I said is transposed followed by complex conjugation. This means complex conjugation for every element. So transpose, you could check that this Y transpose X transpose, oops. You could also see that you could bring the complex conjugation inside. Therefore, this is Y dagger, X dagger. These are all like, if you want, you just write down matrix multiplication, do the transpose term by term. You see that because these are linear operations. This is precisely the content of linear algebra. These nice operations hold. Any questions? By the way,
I have a question.
Yes, go ahead. Yes.
And for any vector, it must have an adjoint, right? For
Every
any
ket.
operator, it must have an adjoint.
Every ket, you mean? Yes. And every bra as well. Every ket, every bra, they have an adjoint. Yes.
Yes. Okay.
Yes.
Okay.
Yeah. what is the operate? It doesn't matter ket or bra. What is the operation adjoint? Anyone? It's identity. This already tells you that every matrix, actually, whether it's row, vector, column, whatever, will have a transpose, dagger. Yeah, just like follow the definition. Any other questions? Now, it's unfair of me to present many slides of math without saying a word in physics. Why are we even talking about something non-commutative in quantum mechanics? Do you guys have a guess why I'm introducing this whole construction? All of this Hilbert spaces, all of this like song and dance, is because matrix multiplication is non-commutative. Representing observables by matrices is a good idea because the order matters. What is that analogous to in the Stern-Gerlach experiment? The order matters. It matters whether you first observe Sx and then Sz versus first observe Sz and then Sx. The order of things matter. This is related to that. So when you write xy, so if you have a ket state prepared, when you write xy, it means that you're first performing a measurement observable y, then x. This is the order of things, right? So these are ordered. Quantum mechanics, this Stern-Gerlach experiment, the reason is so well modeled by these matrix multiplication and complex vector spaces and linear algebra is that the order of measurements matter, the order of observables matter, and the simplest way to model that in mathematics is by matrices. This is the core idea behind quantum mechanics. In classical mechanics, we didn't need to introduce this except for one setup. And where do you guys know of operations in classical mechanics where order matters? And there's one place, and over there we also use matrices. Does anyone know? Any guesses?
Rotations.
Rotations, exactly. If you make a rotation around X followed by a rotation around Y, it's not the same thing as rotating around Y first and then X. Same formulation over there. We use matrices. This is, like there are not, mathematicians don't have a million tools in their toolbox. Every time you're dealing with non-commutative things, the simplest thing to do is to use matrices to model them. That's why we're using matrices to model quantum mechanics. Now, you might still have a question, why complex matrices and not real matrices? But we'll get there. Good? Any questions? By the way, how am I doing on time? What time is it? It's okay. I'm running really behind. Let's see. I'm on slide 16 of 26. Doesn't matter. Okay, so now we talked about a bracket as multiplying a bra by a ket like this. The result is a number. What if I change the order of things? I multiply a ket by bra like this notation. What is this object? This is an operator. If you multiply this, you get a D by D matrix. We call this inner product. We call this outer product. The inner product of a bra and a ket is a complex number. The outer product of a ket, bra and a ket is a D by D matrix. But you don't even need to keep track of these names. The notation says it all, right? When you write it like this is a number. When you write it like this, if these are facing out, these are going to be, if this is facing only one way, that's a column vector. If it's facing both ways, that's a matrix. If there's no, this line is not facing outwards at all, it's a complex number.
Sorry, real
Okay.
quick. So you have right under it's an operator. You have the outer product of beta and alpha applied to gamma, and then you have
Yes.
beta and then inner product of alpha with delta. Is that
Oh, yeah, no, that's a typo. Thank you. Thank you. That's a stupid typo. Thank you. Yeah. So when you, this is just follows by matrix multiplication. Ket beta alpha, the outer product as a matrix, as an operator, when you act on delta and gamma, you can see that I mispronounced things. You obtain beta as a vector, column vector, and a number, which is the inner product of alpha and gamma. This is another intelligent thing about notation of the notation of Dirac. You could just pretend that these, you'll see that I'll write this all the time. I can write this. I write this. When I'm writing this, this could be interpreted as an outer product, these two guys acting on a vector, or it could be interpreted as a complex number multiplying beta. It doesn't matter because of this equality. So I write these kind of things all the time, and you'll see that I'll use this to simplify my expressions over and over again. If I had to keep track of these brackets, it would have been painful. These like curly brackets would have been painful. But Dirac notation is very elegant, that you just write them like this. Good. So if you have the outer product beta alpha, take the bracket. Also the bracket, sorry, take the dagger. The dagger acts as if it's acting on them individually. But remember the structure. Oops. We had this, and when I set this, this holds no matter these, doesn't matter, this holds even for non square matrices. So if I take this to be a row column vector, this is a row vector, you could run the similar arguments and you obtain this, right? You first, this guy, the dagger of it comes to this right side, becomes this. This guy, the dagger of it comes to this side, becomes this. So this is the outer product dagger of it. Similarly, the same operation, if we act on the bra, it holds. So I'm going to be writing these kind of expression. Oh, actually, sorry. No, this is, I had another point here. So now let's do this. Let's act on the right of a ket by an operator, and then take the inner product of it with a bra. That is like this. That's like a row vector, a matrix vector, a matrix and a column vector. I can view it as this guy acting on the right and then taking the inner product, or this guy acting on the left and taking the inner product, right? Therefore, I'm going to represent this. Yes. Questions? Okay. I'm just going to represent it this way. I have the choice of pushing this, making this act on the left or acting on the right. Good. What is this? It's a number, right? By the way, does anyone know what this is? Like another name for this?
Matrix element.
Exactly, matrix element. Why is that? Because if I pick alpha to be, for example, 0, 0, I don't know, let me do two-dimensional. 0, 1, and this is x11, x12, x21, x22, and then this one, pick, for example, this. It'll pick one matrix element for you. You can tell which matrix element. I'll leave it to you guys to work this out, but these are matrix elements. Good. So I'm going to be writing it this way. And now this is a complex number. So I can take this complex conjugation. Complex conjugate. That acts in the following way. That is equal to flipping this. This is really like, you could convince yourself that if you take the dagger of all of these guys, one by one, the order changes and becomes alpha. You just bring this guy this way. becomes X dagger, beta comes here, and you get the convoluted conjugate.
Sorry, quick question.
Yes.
If alpha and beta are not basis vectors, then how is it still a matrix element?
It's a matrix element in some funky basis.
Okay.
Some funky, yeah, like if these are not orthogonal, then we still, as physicists, we still call it matrix element. Like it's just a word that we use.
I see.
Good. That was a very good question. All right, any other questions? Let me see, actually, I have to be strategic. We have a couple of minutes left and I want to summarize. Okay, I'm gonna go through, oh, this is a very important thing. Yeah, let me pause here, summarize and ask for questions. I went way slower than I expected, but it's all right. So be it. All right, so what did we discuss today? Last lecture, we ended on this, we got a hint from the comparison between Stern-Gerlach and this wave polarization of light, that we could model, perhaps model quantum systems using vector spaces and quantum observables using matrices. And the element that I tried to identify today is that the point is that matrices are good because they are not their multiplication, because they have an order. Their multiplication is non-commutative. In classical physics, it didn't matter if you measured, if spin was a classical concept, it wouldn't have mattered whether you're measuring them in different order. But here, the order matters, and that's why we're using non-commutative things. We said complex Hilbert spaces. I have not explained why complex numbers come into play. That's a mystery for now, but I've motivated it. I'm building framework, and we're going to get there. We define the Kets space. Those you can think of as complex vector spaces. Bra space, it's a one-to-one correspondence between them. We define the inner product. We define the dagger operation. We explained why the transpose has to be accompanied by complex conjugation to define the dagger. That is because of the desire that inner product of a vector with itself, a ket with itself, becomes a measure of length. We don't use the word length in complex Hilbert spaces. We called it a norm, right? Because norm had to remain positive, non-negative, the same way that length is non-negative. We had to introduce dagger as transpose followed by complex conjugation. We talked about matrices as operators. We defined self-adjoint or Hermitian operators. These are equivalent terms for finite quantum systems, finite matrices. So the point is this: every observable is a Hermitian operator, and every Hermitian operator is a matrix. So previously I said observables are operators, but not all operators are matrices. Not all operators are observables. The one-to-one correspondence is between observables and Hermitian matrices. Okay. Why Hermitian? Because we're going to see in the next lecture that the eigenvalues of Hermitian operators are real. The eigenvectors with different eigenvalues are orthonormal. So we're going to get there and we're going to discuss that. So the next lecture is going to be starting with the theorem that we're going to prove and explain the underlying logic behind the idea that we're going to be using not every operator, not every matrix as an observable, but only Hermitian operators or matrices as observables. All right, I'm going to stop here. Are there any questions?
I have a slightly tangential question. In QFT, we say it's hard or like we I guess motivate the use of fields because there are no finite dimensional representations of unitary representations of the Poincare transformations. But it seems like in quantum mechanics, we're often dealing with infinite dimensional representations. So what makes a QFT harder than QM?
Let's not discuss quantum field theory. That's a very, very long story. But the short answer to your question is that quantum mechanics is quantum field theory in 0+1 dimensions. And it turns out that the 0+1 dimensional case is the hardest case. That's a long story for another course that I'm teaching in a couple of hours. But yeah, any questions about today's lecture or quantum mechanics? Okay, if not, please, those of you guys who want the course equivalency, stay on Zoom, and the rest of you, I'll see you guys on Tuesday. Thank you so much.
Thank you.
Thanks.